By now, you have seen shock waves caused as a result of massive explosions, volcanic eruptions, high-speed projectiles, and objects moving at supersonic speed. To quote it simply, shock waves are formed when a huge dissipation of energy occurs with the shortest possible time. So, which is the simplest example that strikes your mind when I say large energy dissipation in the shortest time interval? Imagine blowing air into a balloon. What happens when you end up blowing more air than the balloon can contain? It bursts, causing a large energy dissipation in the shortest time interval. A shock wave can also be simulated in a laboratory using a device called shock tube. I am going to teach you one of such shock tube called Reddy's shock tube, named after its inventor Professor K.P.J. Reddy. But before I explain its working, I would like to draw your attention towards how the Reddy's shock tube is constructed. Reddy's shock tube, as you can see, is a long metallic tube divided into two sections. On your left hand side, you see the driver section, and on your right hand side, you see the driven section. Why do you think were these two sections named this way? Well, to answer that, look a little further to the left of the driver section. You will see a small piston there. This piston drives the gas in the section to your left in such a way that it impacts the gas present in the section to your right. Hence, the section which drives the gas from one section to the other using a piston is called the driver section, and the section where the existing gas gets impacted due to the infusion from the driver section is called the driven section. This also explains why the gas in the driver section is called driver gas and the gas in the driven section is called driven gas or test gas. Isn't it obvious that there has to be some medium of separation between the two sections of tube that will hold off the gases in their respective places till the driving action begins? So, pay close attention to the thin layer between the two sections called the diaphragm. Now slowly shift your attention atop the driver section. See that small meter-like instrument? That is the pressure gauge. Finally, I want you to look to your right, that is atop the driver section. Those two transducers are nothing but the shock wave sensors. This completes the schematic layout of Reddy's tube. Moving ahead, I'll tell you about the function of each component in this device and also explain its working. Now let's see how Reddy's tube works. But before we dive into the working, I want you to recollect one of your high school physics concept, which explains the relationship between applied force, surface area, and pressure. On the application of an external force, if we keep decreasing the surface area, the pressure acting on the surface keeps increasing. Keeping this concept in mind, let's go back to the Reddy's tube again. The tube is divided into two sections, where the driver section covers 40% of the area and the driven section covers 60% of the total area of tube. Now, the driver section is filled with high pressure gas and the driven section is filled with low pressure gas. The separation of two sections is done using a diaphragm, generally made of materials like plastic or mica. When the piston is pushed inwards, the surface area accommodating the driver gas reduces, resulting in the increasing pressure of driver section. Remember the high school physics concept we just revised? As we keep pushing the piston further into the driver section, the pressure keeps on increasing to an extent that it ruptures or breaks the diaphragm. The diaphragm breaking is very similar event to the balloon example we took in the very beginning. Remember that pressure gauge I told you about when I was explaining the construction? Purpose of that pressure gauge is to record any changes occurring across the shock tube during the process. Do take note of this. Once the diaphragm is ruptured, the driver gas rushes into the driven section, causing large energy dissipation in shortest time. And what happens when a large amount of energy is dissipated in the shortest time possible? Shock waves are generated. These shock waves, which traverse along the length of driven section, can be of two types: primary shock waves and the shock waves generated as a result of reflection of the primary shock waves against the wall of shock tube. Remember those two sensors placed atop the driven section? Yes, these sensors S1 and S2 sense the pressure from the shock tube as signals. Now, as you know, sensors converts one form of energy into another. These sensors too capture the changes in pressure and convert on a cathode ray oscilloscope. The recordings obtained on the CRO can help deduce important parameters like shock arrival times, changes in temperature caused as a result of changes in pressure, and Mach number.